Okay, well, I think maybe I think that there's a bigger chance of proving this one than the other conjectures, like three-sum and all pairs shortest path and all these algorithms problems, right? I don't think there's any chance that we're going to prove those unconditionally anytime soon, right, given the state of the art in circuit lower bounds and Turing machine lower bounds. So, but anyways, so what is the online matrix vector conjecture? I guess it had come up a couple of times over the last few days. Just kind of start slowly and maybe remind you what the motivation was for introducing this problem. So to do that, I guess I'll start with another conjecture that Amir also mentioned in his tutorial, which was this combinatorial Boolean matrix multiplication conjecture. Right, so what is this? And this is the one that the online matrix vector conjecture is supposed to replace in some sense. So combinatorial Boolean matrix multiplication. So what was the problem here? The problem was that the input, so it's an algorithmic problem, right? You're given two matrices, A and B, and a Boolean, and then you have to compute the product of A and B, where multiplication is and addition is or. Right? So the Boolean simmering, which means that it's basically the product is just. So entry I comma j of C is just you can think of it as a set disjoint, or a set intersection between the ith row of A and the jth column of B, right? So the entry is 1 if and only if the two binary vectors have a 1 in common, at least one in common, right? So this is the Boolean matrix multiplication problem. And the conjecture that this online matrix vector multiplication conjecture is supposed to replace is that it's assumed that any combinatorial algorithm for this problem needs cubic time, right? So that's the conjecture. And I guess the thing we don't like about it is that there's this notion of any combinatorial, so there's this undefined term here, combinatorial algorithm must use n to the 3 minus little of 1 time, right? That's the conjecture. And of course, the problem is that you can actually solve this using fast matrix multiplication. Just do it over the integers, and you can just see if it's a non-zero, it has to be a 1 over the Boolean simmering. So you can solve it in n to the omega time. But the problem is super convenient for reductions, right? You can make many simple reductions from it, and I guess Amir already showed a bunch. I think I'll still do one just to warm up today, take it slowly. So let's do one reduction from this to a static data structure problem. Okay, so here's a static data structure problem that I looked at a long time ago. I think it's actually one of the first problems I ever looked at in my PhD. So it's called range mode. And back then I looked at it at an upper bound side. So the input is an array of numbers, or integers. Think of them as labels or something like this, right? So there's integers in the array, and some of them can occur multiple times. Maybe you have, to make it interesting, let's say you have 2 2s and you have another 5 here. Okay, so you have an array like this, and then you have to pre-process it into a data structure. And then the query to this range mode problem is a pair I and j, and then you have to return the element that occurs the most times in the subinterval from I to j, right? So in this case, the answer would be the element 5 because it occurs 3 times in this subinterval. You'd also have a query from here to here, right? And then the answer would be 2 because it occurs twice in this subarray, right? So that's the range mode queries. I guess you can, maybe one motivation for studying it, I don't know, maybe you have a shop, and whenever one of the people working in the store sells something, you write their name in this array, and then you can ask, oh, who sold the most from Monday to Friday, and something like this. I don't know, that's one.
In the definition of the problem, how do you break ties?
You can return anything you want, anyone you want, yeah. Good. And so we can prove, if you believe this combinatorial Boolean matrix multiplication conjecture, you can prove a lower bound on the pre-processing time plus the query time for this problem here. So let me show you how you can solve combinatorial Boolean matrix multiplication using a data structure for range mode. Right, so I think it's a pretty cute reduction. So what do you do? So you're going to, the array A is basically going to consist of these chunks. The first half of the array is going to correspond to A, and the second half is going to correspond to B. Right, and we know that there's, of course, at most n, let's see, Okay, so we're just going to have an array here. One of them is going to correspond to the first row of A, the second row of A, the third row of A, and so on, right? So this is going to correspond to the first row, second row, so on. And then the second half of the array is going to correspond to B. So these are going to correspond to the columns of B, B1, B2. And the idea is that you want to use a range mode query, basically one query for each pair over here, and the answer to that query should determine whether the ith row and the jth column have a 1 in common. That's the basic idea. So how do you do? So if I have a row here, look at the first row of A, I'm going to take all the indices where I have a 1. I'm going to write those down at the end of the array. So maybe this is the first column, the third column, and the fourth column, right? So I'm going to write 1, 3, 4 over here. I'm going to, the second row here, I'm going to have 2 and 3 placed here at the end of the array, and so on, right? And I'm going to do the same for the B array, or the B matrix here, so maybe this is 1, 1, 0, 1. So here the column, I'm going to pick the row indices where I have a 1. So I'm going to pick 1, 2, and 4. And here I'm going to put them in the other end of the array, so 1, 2, 4, at the other end of the chunk, so to say. Now, I guess you can already see that kind of if I wanted to figure out whether the ith row and the jth column have something in common, I'm going to try and put the query something like this, right? And what we see is, of course, right, the 1 is in common with the 1 and the 4 is in common with the 4. It's kind of corresponding to this bit, this bit, this bit, and this bit both being there, right? So as soon as there's one element in common here, we know that we have to put a 1 in the matrix, right? So now we just want to make sure that these are the ones that will be the majority of the mode elements if we ask the range mode query. And the only idea is just you take, okay, so you look at all the columns that I did not put in already. I'm just going to put them here in the beginning. So here I'm going to put 2. And here I'm going to put 1 and 4. And here I'm going to put 3 in the last chunk, right? Because then the observation is that all the ones that you completely contain, you have all the elements there, right? 1, 2, 3, 4, 5 up to n. So they're all there. So, and this is the case for everyone who's fully inside the interval, you have all the elements. So they don't change the mode, right? So after, if I kind of look at the query from here to here, right, everyone occurs equally many times. So it's just, so this, if there's anything in common, you'll have 2 plus the number of fully spanned things as your mode, and otherwise you'll have 1 plus the number of fully spanned. So the Q reduction, and I guess you can see beforehand you kind of need to store, where does this separator start and where does this separator start, but that's a constant time lookup in a table, so that doesn't matter. You can easily do this. And you can also, this returns the element 4. Now you need to know whether 4 occurs twice or 1 extra time, right? You still need to check whether it's there twice or 1 extra time. But you can store a hash table or something like this that tells you where's the 4 inside this block, where's the 4 inside this block. Then you can just go and look, is it in this part and this part here. So you just need to check that as well, but that can also be done in constant time. Okay, so this means, right, so you take this array, you build, I guess this is an input to the array of size. The array size is n squared, right? And the combinatorial Boolean matrix multiplication conjecture, I guess what is the number of queries that we're doing, right? It's also going to be n squared. So that's also n queries. So I guess n times the query time plus the pre-processing time on an input of size n has to be at least, I guess, n cubed, something like this. And then I guess you can write n cubed as just capital N to the 3/2, right, something like this. So which means that either the query time is square root n, where n is now the size of the array, or the pre-processing time is n to the 3/2. And that's a matching upper bound actually for this problem. Okay, so I think this is another reduction that I think is kind of cute, you could also do from combinatorial Boolean matrix multiplication, right? But the problem is that, again, as already mentioned, you can do faster with fast matrix multiplication. And I guess this is one motivation for introducing this online matrix vector multiplication conjecture, as already been said a few times. So maybe let me just Yeah.
So if it so happens that omega is not 2, then this gives a static data structure lower one which is more than 1, like more than log n.
Yeah, if you believe the
Why does combinatorial, I mean, even if I had a fast matrix multiplication here, I shouldn't be able to do this thing better than n to the omega.
Right.
Instead of n to the 3/2 there, I have some function of omega.
Yeah, yeah.
Which is more than 1. The important bit is that it will be more than 1 as long as
Yeah. I guess if n to the omega, if omega for Boolean matrix multiplication is more than 2, yeah. Right. So maybe Boolean is even easier than normal matrix multiplication. That could be the case, I guess. But yeah, you're right. If you had an unconditional lower bound for this problem, you would also get an unconditional lower bound for this. For the if you had an unconditional. But I guess the problem is for any problem where it's an algorithmic problem, offline problem, we don't have anything that resembles any lower bounds, right? I think.
Improving unconditional lower bounds for omega is hard as
Sure.
Right. Yeah. But it's true. So I think that there's a bigger chance that we can just use data structure techniques to prove an unconditional lower bound over here directly. I think that would be more likely. But yeah. Okay.
So that 10 to the power 3/2 is the lower bound you want to prove it?
Yeah, I think actually that's the lower bound that you can also match this with an upper bound. Yeah, there are upper bounds.
No, but that's what I was saying. If you prove the data structure lower bound, then you're proving omega is not 2. No?
No, the reduction doesn't go the other way, right?
That's an online problem.
Yeah, the reduction, yeah.
I think the whole hope for proving the data structure lower bounds is precisely because it's an online problem.
Yeah.
Whereas for offline problems,
Yeah, I guess that.
circuit lower-
Yeah, exactly. It's circuit lower bound. Yeah, so I think we have more hope of proving these ones, and I guess that's also why I guess one reason for liking the online matrix vector conjecture. There's actually some hope of proving it unconditional, at least more hope than the other things, I think.
Michael, what is PP?
Pre-processing time. Yeah. So the pre-processing. So here, like because you go from this offline problem, there's a pre-processing time to build the array, and then the query time afterwards to do n queries.
So I missed something. I heard you responding to something by saying that something was an online problem. But I saw I thought both of these are static.
Yeah. Yes. Okay. So again, you can still think this range mode problem. Even if you build a data structure, there's still hope of proving. How to say? Like the queries still like in range mode, you don't know the queries in advance, like the I, j. So it's kind of online. Like it's a static data structure. Whereas here, you know all the pairs of queries. You know you're going to ask all n squared pairs. Over here, you don't know in advance which I and j's that you. Right. The data structure has to solve any query I and j, even if you don't know it in advance. So in that sense, I guess there's some hope of proving that one using actually there is already a log over log lower bound for this problem in the subproblem, unconditional lower bound on the query time. The lower bound is the query time is log n over log space word size over n. Right. So this is the lower bounds that Watching did. I think it was my second paper as a PhD student. We proved this for this range mode problem. Using basically this reduction just with much smaller sets instead of sets of size square root n. We had sets of size polylog n, and then we can do a reduction from this Mihai's. If you know the paper, this reachability he has this paper about reachability oracles in the butterfly graph, and there's some lopsided set disjointness problem and stuff. So it's connected to that. No, this unconditional lower bound we prove, yeah, but it's only logarithmic, not root n, so it's much weaker, right?
But, okay, so one could hope for. I don't see how to do this.
Yeah.
I mean, you could hope for a reduction the other way.
Not if you have to answer the queries immediately when you get them, right? It's not clear how you could translate the other way. Here you have to, whenever a query comes, you have to answer it before you get the next query, right? In the static, it's in a data structure, so it's not clear how to translate it back again.
Like if you have a
I see. I'm sorry.
Yeah.
You're allowed to use when you're doing the algorithm.
Yeah.
You're allowed to use the work that you did for answering one query, essentially.
Yeah, exactly. And you know already what queries I'm going to ask. I'm going to ask all n squared pairs.
You can ask them in whatever order you want.
Yeah.
Okay.
Exactly. Right. Okay. So, let's do the online matrix vector multiplication conjecture then.
Just one last question here.
Yeah.
How does the combinatorial word means in the data structure?
Yeah, what does it mean? Yeah, it's a little unclear again. Maybe the data structure doesn't do fast matrix. yeah, it's not even clear, right? What does it mean that it doesn't do fast matrix multiplication? Yeah,
By the way, that,
Sorry,
that-
what was, I didn't hear.
yeah, what does a combinatorial even mean for a data structure when you pre-process something and then query it? Yeah, I guess it supposedly means that you don't use fast matrix multiplication during pre-processing and you don't use it during query answering, I suppose. So it's still a little weird, right? That's why we don't like it, I guess. So let's do the online matrix vector instead, and then.
Does it make sense to actually define combinatorial as something that works online?
I don't know. I don't know. Maybe you had some definition of combinatorial in some paper.
Well, I did, but I
You don't like it.
well,
Yeah.
it covers some algorithms.
Yeah.
I was making this argument, but I don't want to interrupt your talk later on.
Yeah.
I want to mention that I can give a good argument that fast matrix multiplication is a combinatorial algorithm.
Okay, that's good. Good. So okay, so let's do the one that Amir already mentioned it. So the online matrix vector multiplication conjecture, matrix vector, OMV. So the idea in this problem is just that you don't give the matrix B in advance, right? So so it's more like I guess it's actually a static data structure problem, but it's often used in the dynamic reductions as well to the dynamic problems. So the input is, I guess, the matrix A, if you will, like this n by n Boolean matrix, and so on. And then you get queries, so you're gonna get n queries, or maybe I can call them B1 to Bn, so one at a time. So think of the columns of B, and then the goal is to output a BI before seeing BI plus 1. Right? So it's basically a static data structure. Pre-process A into a data structure, and then your queries are matrix vector multiplication queries. Right? Good. And then the conjecture is that over a sequence of n queries, the amortized, so the total amount of time, or maybe let's write it like this. The total time n to the 3 minus little of 1. Right. That's the conjecture. Okay. Even, this is actually going to be important, even for randomized algorithms, randomized, let's call them algorithms or data structures, with failure 1/3 or something like this. Right. So the conjecture is even randomization does not help in this problem. Yeah.
So, how much pre-processing time are we giving?
This is the total time. So this is
Including
yeah, yeah. So this includes pre-processing. What I'm going to show you is that you can actually allow for arbitrary polynomial pre-processing time. There's a reduction to get to that. That comes for free. Yeah.
And failure will be failure to compute any one of these.
Yeah. I guess as soon as you have one that's correct on each one individual probability 1/3, you can do a logarithmic number of copies and do maybe, then you can see if the majority element is something like this, right? And so 1/3 is enough if you only care about polynomial factors. You can always do independent repeats.
So but if I give you a lot more pre-processing time,
Yeah.
do you know how to, is it helpful?
No, that's a reduction. Or maybe super polynomial could potentially do it.
But we don't know, we don't know anything non-trivial.
I'm going to show you. We know some non-trivial things. I'm going to go over the best known upper bound for this problem. All right. Now maybe let me. Okay. Of course, we should credit who. So it's by Monika Hensinger, Sebastian Klinninger, Danupong Nanonkai, and Thatchapol Saranurak from 15, I believe. Right, this is when the conjecture was made. Okay, and maybe, okay, so a bunch of things I want to show about this problem. One of them is that you can allow for polynomial pre-processing time, if you will. So maybe let me start with that. Yeah.
Why you cannot boost the probability of success of this thing by running it in parallel?
Let's see. So I guess it depends on exactly what one means by failure 1/3. If you say each query in the sequence is correct with probability 2/3, then if you run independent copies by Shannon, right, most of them are going to. What?
Like, isn't
Okay, so if you change the query based on the answer you output, then maybe not, right? If the whole sequence is fixed in advance, but you just, I guess the formulation is that there are these queries, they come one by one, but if they're chosen adaptively, then maybe maybe.
But the adversary is not allowed to see.
Yeah, that I got. I was.
But I guess the adversary cannot do, if you do a majority of, even if the first one, if you fail with probability super, like 1 over n to 100, you're always going to output the same, so the adversary cannot adapt. It's going to be the same fixed sequence. So I guess it also works against an adaptive adversary, right? Because then you know as long as you succeed in the first one, the adversary is going to do the same on the next one. So yeah, I think it still works.
But as they do repetition, like for each repetition, it's going to be a different output.
Yeah, but if it's correct with probability 2/3, right, there's going to be a whole vector that's that's going to be the right one with overwhelming probability. Yeah, so I think that's okay. So randomized algorithms is also hard. Okay, and let me start by showing that you can allow.
Okay, so I lost something, this discussion of adaptive versus non-adaptive adversaries.
Right.
What should we be thinking about now?
Well, I think it was just saying whether this whole thing, if you can do the parallel repetitions, if you have an adaptive adversary that can choose the next query based on the output you make, whether you can still do the parallel repetition. I think that was basically the question. But you still can, right? Because if you just boost so that the first one you're correct with, except with probability 1 over n to the 100, you're always going to output the same, so you know what the next one is. So I guess you can do a union bound over the whole sequence of, if I'm going to answer correctly, what is the adversary going to do? And
I'm saying, but when you're talking about this conjecture,
yeah.
are we using, is there an adaptive adversary?
I think the original formulation is just that there's a fixed sequence B1 to Bn, that you don't know it in advance, but it's fixed. I think that's the formulation of the conjecture. But I think if you have an algorithm that solves this, it also works against adversaries that choose them and so on. So I think, good. Okay.
Is there a reason why it's always posed as B1 through Bn? Because one could argue that you could give a similar conjecture with just, instead of having n queries, just have one query out of many 0, 1.
Yeah, I think I think that for many of the reductions, it's convenient to say, I think that even if you have a whole lot of queries that you're going to answer in total, then the total time has to be large, right? So that so I guess it's a stronger conjecture because potentially, I don't know how, because you don't see them other than one at a time, but in some way you could perhaps use some sort of amortization and show that most, in an upper bound, right, maybe you can show that most of them are going to be easy, but a few of them could be hard. So this is a stronger conjecture in the sense that saying even over n queries, each of them is going to take n squared on average. Right? Actually, the best upper bound is actually amortized, so some of the queries are going to take n squared time, and some of them are going to be faster. Most of them are going to be faster, but a few of them in the beginning are going to be slow. So for the upper bound that we're going to see, it's actually important that it's a whole sequence of queries that you have to answer, and that the conjecture still says this takes cubic time. Okay. Maybe let me also say at the time the conjecture was made, the best upper bound was n cubed over log squared n by Ryan Williams from, I don't remember when it was, but Ryan Williams had an n cubed over log squared n upper bound for this problem, right? So it seems very fair to conjecture that you cannot do this, right? So that was the upper bound at the time. Okay, let me show you that this conjecture alone implies that you can also allow arbitrary polynomial preprocessing time, and still the total time for the rest of the sequence has to be cubic. Right. So let's say I have let's call it T processing of n. So for n by n matrices is, let's say I have an algorithm that runs in n to the c time for some polynomial c. And how do I want it? Let's say that the query time to answer all the remaining n queries, and let's say n queries of size n, let's say is some n to the alpha. And we want to prove that this last term still has to be cubic, right? Alpha still has to be 3. That's what I want to argue that this follows from the other one. And the basic idea is to say, okay, I have the original conjecture. I have an n by n matrix, and I want to answer n queries on it. What I can do now is I'm going to take the matrix, and then I'm going to cut it into a whole bunch of smaller matrices, like this, right? So each of these small matrices are going to be, let's say, S by S, something like this. And now I'm going to take this data structure and build it on each of the little pieces here. Right? So the total time, right, so how many are there? There's n over s squared little pieces. And in each of them, I'm going to do s to the c time, right? So then I get n squared times s to the c minus 2. And you can see if you do put s small enough, this is less than cubic, right? So I can just put these small matrices really small. So maybe I can put them, it's sufficient to put them to n to the 1 over c. Then I'm subcubic in the preprocessing time. And what is the query time? So how can I now answer a query, right? So if I have a query like this, I can cut this query into little pieces of s each. And you can see that you can kind of combine the answers. I can answer this query on this matrix, this one on this one, this one on this one, this one on this one. Right, so I get one on each of these little ones. And that's going to answer one of the queries. So what do I get for the remaining time, right? So I'm going to have n queries. For each of those n queries, I'm going to have these n over s squared subproblems. And on, well, maybe this notation is, let me say that this is a time to answer one query on a matrix of size n instead. Let's say that, just to make it a little easier. This is time to answer one query on an n-side matrix. So each of them I'm going to do an s to the alpha here, right? Something like this. Right, that makes sense. So this gives me n cubed times s to the alpha minus 2. Right, is that correct? Right, and you can see since s is polynomial in n, the conjecture implies that this alpha has to be at least 2, otherwise I've gained a polynomial factor. Right, so still you have to use quadratic time per query that you ask on the little ones, right? So
This actually looks like it works to reduce the preprocessing down to.
yeah, you can reduce
quadratic.
you can reduce the preprocessing time down to n to the 2 plus epsilon. Yeah, you can always reduce the preprocessing time. Of course, the advantage you have over quadratic query time also goes down similarly, but as soon as you're subquadratic in the query time, you remain subquadratic in the query time. So that's why if this conjecture is true, right, then you can still allow for arbitrary polynomial preprocessing time, and still the remaining sequence has to take cubic time to answer. Okay. So this is like even with polynomial preprocessing. Right, processing. And here total time is the time for everything after preprocessing, right? And then it still holds. And if you will, right, this does not have to be n by n by n. You could also look at n1 by n2 matrices, and then you have, I guess, n3 queries at the end. And if they're all polynomially related, you can do a similar cut into small matrices, and then the conjecture says that it has to take n1 times n2 times n3 to the 1 minus little of 1. Right, that you can do the same just by cutting it into little pieces again of the right shape, and do the same argument, right? So.
By the way, this trick holds for any decomposable data structure.
It does, yeah. As long as the conjecture is such that you cannot do anything non-trivial, then you can always kind of.
You can always
Yeah.
enter the 100 preprocessing time.
Yeah.
apply it to
Smaller pieces. Yeah. That's right. That's right.
This trick was actually mentioned in Williams' review.
Yeah. I guess you're right. Okay, good. So what else do you want to say about this problem? Okay, maybe let me just give one reduction again, just to a version of this range mode problem where you don't get the combinatorial part of the conditions anymore. So just because it was a fun problem. So what's the dynamic version of? So let's call it dynamic range mode. Right, there you have an array A, and you can append entries to the array, and you can ask range mode queries, find the most frequently occurring element in a subarray. And the reduction is basically the same, right? During preprocessing, you build the first half of the array, right, where you take, again, you take each of the rows here, you put you put the entries where you have a 1, you write them in the right-hand side of the, what was this, 1, 3, 4, and you write the entries that you don't have in the beginning of the chunk, and you do so for all the rows. When you get the matrix vector query, so you get a query B, right, so then you look at where are the ones in B, you append a block here, we put all the indices of the rows that you have a 1, you write them here. So again, this would be, if you get the first one, you put 1, 2, 4 in the beginning of the block, and you put a 3 here, right? And then you just ask a query. You have to output the matrix vector product. So you're going to ask this query against the first chunk. You're going to find where this one starts, right? You're going to ask this query. You're going to ask this query. You're going to ask all those n queries, and this computes the matrix vector product, right? So I guess this proves the same law bound as before on the time for updates and queries. So let's say again, so this is an n by n matrix, right? The size of this array is going to be n squared, and you're going to ask a total of these. The number of queries you're going to ask is going to be n queries, I guess, in total, right? So yeah, you're going to ask n squared little ones. You're going to ask all these queries on an input of size n. And then you're going to do some updates as well, right? You're going to build you're going to build an array of size n in total, right? So I guess if you say the time to append one element to the array, then I guess you're going to do n appends on the array or something like this, right? If tu is the time to do one append. And I guess this has to be, again, n cubed, right? Right, and this is capital N to the 3/2 of 1. So I guess you get the query time plus the update time has to be at least square root of the array size, right? So one of the two has to be at least square root. Okay. So this is one reduction from this problem. I think Emir already gave a lot of reductions, but maybe I'm going to show okay, so there's a reduction from this problem to a more useful. This is still a little tricky, right? Because any query you ask, you have to output n bits, right? So you have to compute the whole matrix vector product. And the conjecture is saying that basically this has to take quadratic time each time you want to output one of those. So you can actually reduce the problem to a 1-bit output problem that still has this quadratic time per query, right? And I think this is a really useful reduction also for going further. So let me do that one. So this was also in this original paper. So this problem here is called this online vector matrix vector. So I guess they call it OUMV, because you kind of get two vectors, one on each side. And I guess the goal is, again, you get this matrix A, it's n by n, and then you get n pairs u comma v, ui vi, and you have to output ui a vi, right? So this is a column vector, this is a row vector, and you have to output this one before you see the next pair, right? And okay, so maybe one thing worth seeing here. So if I have one of these products, right? So the u is like an indicator like this. You have the matrix, you have the v. So what is the answer to the query? You think about it, right? So this thing here is ORing all the columns where you have a 1. So you kind of take all these columns here, and you're ORing them. And then you're looking at all the rows indexed by the 1s over here. And the answer is 1 if and only if there's a 1 in any one of these entries, right? So that's the answer to the query. You're basically asking for a submatrix, subset of rows, subset of columns. Is there 1 inside this submatrix, right? That's what a query is asking for. And what we can show is basically that this conjecture here also implies that over a sequence of n queries on an n by n matrix, it also has to take cubic time in total for this problem, right? So basically each of these queries is going to take quadratic time. That's basically what you can prove. And this is not so clear anymore, but let me try to give the reduction. I think it's really, really clean, like the reduction from this one, right? So let me just ignore this pre-processing time, right? Just because, you know, we can always get from, if it's any polynomial, we can get it down to something that's smaller than cubic. So let's just ignore the pre-processing time. Let's look at the query time to answer one of these queries. Good. So how do we do? So we're given an instance of matrix vector multiplication. Now we want to use the data structure of online matrix vector multiplication to solve matrix vector multiplication. Right. Let me again say that just for simplicity, that the query time for each of the operations is the same for all of them, just to make it a little bit simpler, instead of the total time over all of them. I think it's a little easier to deal with. So let's say,
I'm sorry, could you repeat again what you're about to show?
I'm about to show you that if you believe this conjecture, or this conjecture implies that this problem here, also over a sequence of n pairs, also has to take cubic time. Yeah. So okay, so how are we going to do? So maybe let me erase over here. So, right, so I have my matrix, and now I want to answer these matrix vector queries on it. Right, so this is what I get. And how do I do it? So what I do is I take this matrix, and then I cut it into submatrices again. So I'm going to cut it into root n by root n submatrices of size root n by root n. Okay. And inside each of these, I'm going to build my data structure for online vector matrix vector multiplication on this submatrix that you see in here. Right? Like this. Good. So, okay, let's see now. How can we then answer? So now comes a query. Now we want to compute the matrix vector product using these online matrix vector multiplication data structures as subroutines. So I guess I'm going to again think of my query as consisting of these root n pieces of size root n. And then I'm going to focus on one of these rows at a time, right? So this is like a root n by n submatrix. And now I want to compute the output here, these root n bit outputs. Right? So this is my first goal. But all I can do is ask vector matrix vector queries on these on data structures that I've built in here. And the idea is to repeatedly find more and more of the ones in the output here. Right, so what I'm going to do is I'm going to start by looking at the top corner here. And now, okay, so I get to ask vector matrix vector. So I guess I'm going to think of this one as V, this little piece here. That's my V, and my U here. So maybe let me zoom in on this rectangle. It's here. So I'm going to take this little piece, and the query I'm going to start with the all ones query. Right. So now what am I answering if I answer this query? I'm basically saying, is there any of the output bits here that's 1, right? It's an OR over all the rows of the output, right? So it's going to tell me, is there at least one 1 in the output? Now what I'm going to say is, okay, if there's at least one 1, what do I do now? Now I actually want to find it, and this is, I think, a trick Amir also showed, right? You can actually find a witness to this query answer being 1. So the way I do it is that if this says 1, I'm going to look at my U vector here, then I'm going to partition the ones into 2 halves. I'm basically going to do a binary search for a witness. So now so if I see a 1, I'm going to ask the query that has 1 in the first half and 0 in the other half. Just like this, right? And then if I ask another query, this is going to tell me whether there's an output 1 bit in the first half of this, among the first half of the output bits. If there's not, then I know the 1 bit has to be among the other half, and if there is, I can continue the binary search.
Can you see this as some sort of a sparse recovery you're applying to AV, basically? You have access to AV, you can take linear projections.
Yeah, I guess you could.
All queries at this point.
Yeah, I guess you could say. Yeah, I guess you can say so. So basically, what this gives me, right, is I can use log n queries to find one of the 1 bits, right? So that might find me one bit here. So that's log n queries. Of course, right, I have to see if there are more 1 bits. There could be more in here, right? So what I do now is then I say, okay, as soon as I found one, I can just set that one to 0, put a 1 in everywhere else, right? And now I'm looking at all of the remaining columns to see. And if I find one, I can binary search again until I produce it. So this can result in up to root n queries being made here, right? And if I happen to do root n queries on each of all of these, then it's going to be too expensive.
You're ignoring the login?
The login doesn't matter in the little of 1, right? That's fine. Now, the key observation is that you cannot, it's not possible to have in every single one of these boxes produce root n new output bits that are 1, right? Because they can only in total produce root n output bits here, this whole row here, right? So what I'm doing is I say, okay, I'm starting with the first block. I'm going to find all the 1 bits in the output. Now I have some of the 1s, right? So I know all the 1s that originate from this little piece. When I move on to the next one, I'm not going to start with the all 1s vector. I'm just only going to mask out those that I still haven't found, right? The ones where I don't know it's 1. And then I'm going to keep going, which means that in total, throughout this whole chunk of blocks, I'm only going to find root n of these output bits, right? So let's try to see, so how many of these online matrix vector queries are we going to ask to answer this single one of them, right? So we have root n of, so maybe we can say, okay, so we're always going to ask 1 query on every single one of them, right? So that's going to be, so that's a total of n of these where we're going to ask a query on a size root n by root n online matrix vector query, right? So that's the first query to each of them. So now we're counted for this. And then we also have all these adaptively, the ones that originate from the binary searches. But the observation here is that for each of these chunks of rows, I can only do this root n times, right? Because there's only root n output bits. So that adds another n, and then a log n for the binary search and a query of root n here, right? So this is the total number of queries I do to do the output. Okay. So if this query time happens, so the query time of n is, let's say, n to the alpha, then what is the total query time going to be here? It's going to be n times n to the alpha over 2, right? To answer one of these queries, right? And we know that this has to be, at least when I amortize over, like on average, it has to be n squared time for each of them, right? That's what the conjecture says. They have to take n squared. So alpha has to be 2. Right? Make sense? So I guess in general, this shows that if I can, basically this reduction shows that if I can online matrix vector in, I guess, total time n to the 3 minus c, then I can solve OMV in n to the 3 minus c half. Right? I guess that's basically what the reduction gives us, right? The advantage goes down by a factor 2 when we go into these root n by root n submatrices.
So, I mean, you could do this reduction with a different block size than root n.
Right.
And then, is it easy to see why root n is the alcohol?
Yeah, I think you're balancing the number of these recursive calls that you have to do to find all the outputs, right? So I think it's the balancing between this term and that term that gives you root n by root n. I guess you can maybe get root log n, if you will, here. Maybe that could potentially gain you a little bit. I don't know. But that's the balancing term, right? Because otherwise, if there's too many rows in one of these chunks, then you have to do many of the binary searches on a large matrix, and so you, yeah. So I think this is.
What happens to the reduction if it's over F2, not over?
Then it doesn't. Oh, then it completely. Yeah, then it doesn't work. Right. Okay. Good. Yeah.
So Kasper, this reduction uses adaptivity in U very, very much.
It actually does. Yeah. So maybe for the. Yeah. Yeah, so I guess it's like interesting, I guess, from the point of what you're.
Would be easy if the U is not adaptive.
If the U is not adaptive.
It wouldn't refute the OMV conjecture even in
Right.
the previous.
That's a good question. Well, I guess from the data structure point of view, as long as you can solve any query fast, then I guess you're subject to this. Right? If you maybe from an algorithm's point of view, I don't know, but it seems at least if you build a data structure that solves every possible query fast, then then I don't think it's gonna help.
But didn't the argument you give for high probability bound is that adaptive and non-adaptive adversary have the same power for this problem? But the answer is unique, so as long as the algorithm is correct,
Yeah, the adversary is gonna do the same.
do the same thing.
Yeah,
anyway.
yeah. So it also holds here. Yeah, so it's also with randomization and all of this. Even if you solve this, give a randomized element for this, you still.
No, but it could be like that the time is amortized. That if you answer a lot of queries, the amortized time is good. It's better than one query.
Yeah, but I think the reduction still gives amortized. Yeah, I guess the sequence is adaptive to what you're doing, but as long as you promise that for any long enough sequence your amortized cost is low, then you're not going to beat then you still have to pay a cubic time in total. So, how many breaks are we going to? Do we take a break now?